For future embedded electronics, many sensors and many things, we are moving in this direction. ULP. Right? Ultra low power direction. But then there are some application, ultra high speed application, like terrestrial communication, terahertz level communication, satellite communication, defense application, all those things. You don't care about how much energy efficiency. So you want higher speed, very, very high speed, ultra high frequency application. So you want higher speed, but then your energy efficiency goes down. Because energy efficiency goes, this is power efficiency, right? It goes down because you want ultra high speed, because you want extremely reliable communication. You don't care about how much power you are spending in a satellite base station or any other ultra high frequency application, right? Or if you are basically thinking about an MRI machine, which probably using a terahertz level signal, you don't care about how much energy you are saving, because that MRI machine will be plugged into a very, very reliable power source, and you want the most accurate imaging. Don't worry about how much electricity bill you are imposing, right? On so that is another direction. It is moving for ultra high frequency, multi-gigahertz, terahertz application. So this is trending. This is another trend. But ultimately, in an ideal utopian world, you want to move somewhere here, right? Very high speed, very high energy efficiency. That means at extremely high speed, it will still consume less power. So this is ideal direction scientists and engineers would love to move. So people are exploring what are the materials that can probably will never be here, but can push this top left corner, top right corner. If we can push this to this, that means we are getting higher efficiency, higher speed at higher energy efficiency or lower power consumption. So if we can move this in this direction as much as possible to the top right, then we are improving both speed and efficiency, energy efficiency at the same time. So people are exploring different types of 2D nanomaterials for this, and for this. Also a group of material called TMD. So one of the, as I mentioned, two possibilities. One is do not depend on the KT over Q. So we just explain. One possibility is tunnel effect. The second one is still we want to depend on KTQ, but introduce the concept of negative capacitance. So let us look at the second one, negative capacitance, what we can do. So I mentioned that Saib Salahuddin and his advisor Supriya Datta introduced this concept of introducing negative capacitance inside the MOSFET device structure. So they introduced the idea by introducing an insulation layer here in the gate, replacing the original insulator silicon dioxide with a ferroelectric insulator. That ferroelectric insulator has the ability to display negative capacitance under certain operating condition. With that, if one of them, body or oxide capacitance, one of them becomes negative, this fraction becomes negative. So successful swings will be 60 multiplied by a fraction smaller than 1. Because then it becomes negative, then we will get less than 1 as the factor. So this will be smaller than 60 millivolt per decade. So the concept they introduced by making this one negative. But later they found out that there are some structural, material, and operational difficulties in terms of reliability of the device and longevity of the device if we put the ferroelectric insulator in the gate layer. So then my student's PhD thesis is, how about trying to make this one negative? This capacitance is the capacitance that is active inside the body. How can we make body capacitance from surface to body, this capacitance negative? So we started exploring, well, possibility is, how about let us use SOI device structure. Inside the SOI device structure, there is a buried layer of silicon dioxide as an insulator to separate the active region of the transistor from the rest of the body. Very simple concept. How about do not use silicon dioxide here, use a ferroelectric insulator as the buried oxide, so that the negative capacitance will not be formed here, it will be forming here, because ferroelectric insulator can provide negative capacitance under certain operating condition. So in the fraction, this one is negative, overall any one of them is negative, then whole fraction becomes negative, it will be smaller than 1. So then we found out the modified expression, and this has become our new modified expression with ferroelectric insulator embedded inside the body of the transistor, and now we have a 1 minus the Lars fraction, which is lesser. Now by playing with the value of this capacitance, oxide capacitance over ferroelectric capacitance, by playing with this number, we can make this fraction larger and larger. Overall, this fraction will be much smaller than 1, and this one will go significantly below 60 millivolt per decade, so we have to play with this. So, inside the body, so the equivalent circuit will be, you have oxide capacitance, you will still have a silicon capacitance for this portion, and that capacitance buried inside the body due to the ferroelectric capacitance embedded for this ferroelectric insulation layer. So, if we can control the relative values of these three capacitance, we can control the value of this fraction, and thereby we can control the value of subthreshold swing, how far below it can go 60 millivolt per decade. So, let us look at the concept of negative capacitance first. Forget about ferroelectricity, but what is a negative capacitance? What is a capacitance in general? So you have voltage, you have charge. Typically a capacitance is a what? Parasitic element. The relation between voltage and charge of a capacitance is dictated by Q equal C times V. Voltage times capacitor is the charge stored across the capacitor, right? Typically, it is a linear curve. You increase the voltage, it can store more charges up to certain limit is maximum capacity. The constant of proportionality is called capacitance, right? So this is for a linear regular capacitance. But if any material shows ferroelectric, ferromagnetic property, what does it mean? When it is going up, as we increase the voltage, it will follow one path, and then when it is going down, it will follow a different path, thereby producing a hysteresis loop in the behavior. But at any given point, higher voltage means higher charge, lower voltage means lower charge. Whether it's a pure linear relation or a hysteresis relation. For ferroelectric material, it will show a hysteresis behavior. Hysteresis means appearing a loop in the CV characteristics or IV characteristics. It will follow one path as you increase the voltage, it will follow different path, but every time the slope will be like this. That means higher voltage means higher charge accumulation, lower voltage means lower charge accumulation. But in some case, it is observed that some ferroelectric material will have a hysteresis loop, in such a way that there will be some point the trend will be like this. This is showing the capacitance, the ratio of voltage to current. That means instead of this type of curve, it will have a slightly this, and this is a negative slope. That means the capacitance will be negative. That means for decreasing voltage, your charge will increase. For increasing voltage, charge will decrease. That way, giving a concept called negative capacitance. So, but achieving this condition in the ferroelectric materials behavior is very, very difficult. It is extremely time sensitive, temperature sensitive, and depends on many specific material factors. But several decades ago, physicists theoretically proved that yes, by changing environmental conditions like temperature and material property, a hysteresis loop like this can be achieved in certain ferroelectric material, in certain ferromagnetic material, thereby achieving the concept of negative capacitance. But this was only theoretical proof by playing with their computational model. But actually, they were not able to prove it. But first, in 1998, Mr. Ershaw, he actually experimentally observed negative capacitance in a very, very pristine experimental condition, negative capacitance in certain material sample he tested. But nobody actually was able to recreate their result, or nobody came up with the concept of where to use that negative capacitance, whether that negative capacitance will be useful or not. So fast forward in 2008, Salahuddin and Datta, they reinstated that idea, and they said that, well, this negative capacitance concept, if you can use it inside device structure, we solve the physics problem, 60 millivolt per decade problem. And later, his student, Saif Salahuddin's student, Mr. Khan, he together with Salahuddin, they published this paper in one of the journal, and it became overnight very, very famous. But this paper, 2008, this was considered the pioneer paper that introduced the concept of utilizing negative capacitance inside device structure. As I mentioned, that paper alone landed him 3 job offers in 3 of the top universities in the world.
So still now there is no experimental proof of negative capacitance?
No, there are actually. Saif Salahuddin's group, they did lots of experiment, but the problem is it is in a very, very controlled environment. At regular experimental setup, at the manufacturing level, how to achieve that or sustain that, that is the challenge. But they proved it with different material composition in controlled experimental environment.
I have a question. If it's
Yes.
if it's a controlled environmental situation, we're getting the negative capacitance. But what happened to the real world? If we are not getting the negative capacitance because it's not feasible for us to have that control.
Today is not feasible. So when before 1952, nobody, like for example, the concept of CMOS, a complementary logic, it was given by a British scientist in 1930s. At that time, nobody even thought about transistor. It was a kind of a foreign word, right? the concept of transistor came into existence in 1952. Even then, they didn't know what to do with this transistor. They said, well, it could replace vacuum tube as an amplifier, but the concept of IC, integrated circuit, came 10 years after the introduction of transistor. At that point, they didn't know how to implement a transistor. The concept of original transistor was introduced by 3 big this side gold plate connected together by a group of scientists in Bell Lab. At that point, they did in a very controlled environment with 3 pieces of gold because they wanted the best possible conductor. But then they gradually mastered how to introduce that concept of transistor into a small piece of silicon, and that convert it to an integrated circuit. So it will come in phases. So at this point, people will, in future, they will know actually how to easily achieve. Somebody else probably will come up with the idea. So Mr. Wanless, who wrote the revolutionary paper about CMOS logic in 1963, using the 1930s concept, he was able to see, well, now that transistors are here, integrated circuits here, now probably we can revisit that 30 years old concept, implement this complementary computing logic, right? But then first 10 years, they were not able to, even 20 years, they were able to use complementary logic. They used NMOS only or PMOS only. Intel relied on NMOS only or PMOS only for first 1 decade. And gradually from early 80s, they mastered CMOS logic, right? So with that track record, I hope they will come up with a solution soon. So the question is now, how do we achieve this? As I mentioned, we have to insert a layer of ferroelectric insulator. But the challenge that original inventor group, Salahuddin and Doctors group, they faced, ferroelectric material are very active material. When it touches silicon, it reacts with silicon and it forms a silicate layer. So if I put ferroelectric insulator here, the bottom surface of that insulation layer will react with this silicon channel and form a silicate layer, changing the property and structure of the channel and the gate both. So that will create a stability and reliability problem for the device. So solution is that, well, now the same question arises. If we put insulation layer in the, like SOI device, ferroelectric insulation layer inside the body, then from the bottom surface of the channel, this ferroelectric insulation will react with the silicon channel and change the silicon property. So the solution is, let us put between channel and the solution layer a neutral layer of thin buffer material, which will not react with silicon. So silicon will be protected. But we could put this buffer layer in the gate as well. But then gate thickness will increase. If gate thickness will increase, device drive will become slower. Then you need higher voltage to turn on the device, because the goal is to make the gate insulation as thin as possible, right? So with that design modification, still is theoretical. Nobody can give us a prototype of this device. So the analysis is purely computational, based on device modeling. And we theoretically, based on simulation, we proved that a negative capacitance can be achieved and a 60 millivolt per decade, less than 60 millivolt per decade can be achieved. So the operation of this device, proposed device, we call it SOFFET, silicon on ferroelectric insulator field effect transistor, is very similar to an SOI device. So this is basically what we found. We changed the thickness of that ferroelectric film and other parameters, and then the body factor, we know that it's 1, less, practically it is greater than 1, greater than 6, but we played with the thickness and we were able to theoretically achieve up to 0.2 body factor, so then overall subthreshold swing will be 60 times 0.2 theoretically. So now, why people were trying to achieve all of this? About 20 years ago, US Department of Defense, always US Department of Defense, particularly DARPA, they are very good at setting these lofty, groundbreaking targets. Even if initially it seems like science fiction, but from internet to transistor, US Department of Defense funded research always played a very key role, right? Internet was sitting idle in secret military lab for more than 2 decades before it came into public use. Same thing they wanted to do with transistor. When Bell Lab came up with transistor concept, DoD wanted to make it national secret, but it was a public funded Bell Lab research, so they immediately published it, paper, and Texas Instrument grabbed it, and that's how we became the whole IC era, right? So 20 years ago, DoD published, they started a program called STEEP, S-T-E-E-P. STEEP, subthreshold slope electronics something. Steeper means less than 60 millivolt per decade. And they set a target to go down to 20. So if you can go from 60 millivolt per decade to 20 millivolt per decade, that means you are basically gaining almost 300% reduction of 1/3, like you are just 1/3, almost like 200% reduction of energy consumption for the same speed, right? So signal speed will increase manifold if that can be achieved. So they have this goal of 20 millivolt per decade subthreshold swing. So this is an SOI device. This provides high on current, low off current. So I on-off ratio will be higher, which is the desired property, and the structure and operation will be very, very similar to a regular SOI device. And these are some additional computational based analysis simulation, how different parameter of this device with the change, threshold voltage as well as subthreshold swing changes. So theoretically, if this type of negative capacitance based device, whether at the gate level or at the SOI device structure level, we can go below down to 20 millivolt per decade, crossing the target set by DoD. So in the negative capacitance based devices, there are 2 options to implement it. The original option is called gate stack negative capacitance device, because they propose that we put a ferroelectric insulation that can exhibit negative capacitance as the gate insulator, replacing silicon dioxide. So that design, that concept is called gate stack design. Later, we introduced, this is called body stack design. That means the ferroelectric material insulation will be stacked inside the body, not in the gate. But either way, the whole idea is to make that capacitance ratio negative, to make the body factor less than 1, to make the subthreshold swing less than 60 millivolt per decade. So these are the numerical analysis to get the IB characteristics of the proposed device. As you can see, the body factor, we're able to, for this one, we're able to go down to 0.33 from 1. So what are the issues for this type of proposal? This is just a high level line diagram of this proposed device. Number 1, as I said, silicon ferroelectric interact and it forms an intermediate silicate layer. It changes the structural property of the device. One of the biggest challenges is the property of ferroelectric material is highly sensitive to temperature. Slightest variation in temperature will change its behavior and it will be very difficult to achieve the negative capacitance. Desired negative capacitance at the desired amount and desired time will be very, very difficult. Also, achieving ferroelectricity from ferroelectric material at nanoscale thickness. That is another challenge. And to protect the silicon formation, we have to find a buffer insulation layer that will be there. Steel will provide very high dielectric constant and insulation property. Also, it will be stable against thermal change. Also, it will not introduce additional leakage. And it will not interfere in the operation of the device. So finding suitable buffer layer to prevent the challenges of ferroelectric material to silicon insulation, silicon reaction, that is also another issue. So, if we want to, let's kind of summarize, we talked about new architecture, that is negative capacitance based device instead of MOSFET. It is expensive, difficult, suppressor swing. Initially, before the negative capacitance based device introduction, some of the new different versions of MOSFET they introduced, it has even worse suppressor swing because at nanometer scale, suppressor swing actually increases. Silicon based chip now, due to this problem, it is reaching its limit in terms of physics, a physical limit and performance limit. Band-to-band tunneling device are being explored, but still the problem is it has very low on current, and on current to off current ratio is very low, and still we don't have clear control on the tunneling phenomena. You need very, very precise control on the tunneling phenomena to achieve certain current at a certain voltage. So we explored some option. People are also exploring other option. One is impact ionization based MOSFET, IMOS, another new technology. Ferroelectric material based MOSFET that we have talked about. Two options, one is gate stock, one is body stock ferroelectric material. Still, it has some problem like short channel effect and leakage current, high leakage current. So, to overcome this ferroelectric material, this is like gate stock. So, our proposed design theoretically provided higher speed, lower settle voltage, higher integration capacity because of the low off current, because it's SOI device, so inherently it's low off current and low leakage and high on current. So it has all the advantage of SOI device plus the advantage of having negative capacitance like a ferroelectric MOSFET, a gate stock ferroelectric MOSFET. But again, these are purely theoretical analysis. There is no way to validate it because we never did any experimentation, because nobody knows actually how to process and put ferroelectric insulation layer inside the device structure. Manufacturing process is not there.
But the research is ongoing, right?
Research is ongoing, as I said, the entire Saif Salahuddin whole group, and he's a student at Georgia Tech. Both are gurus of negative capacitance. So if you search their
Asif Khan?
yeah.
I know.
So yeah, they're expert in ultra low power design. Transistors that will operate in subthreshold region. Like Purdue has one of the strongest group in ultra low power design. Dr. Supriyo and Kaushik Roy, he considered himself the godfather of ultra low power design. He has like all the books, he has like thousands of citations on his anything to do with leakage current. I think he produced nearly 50 master's thesis and PhDs just on working on leakage and ultra low power design. So that group is, so one of the important branches under the ultra low power design umbrella is to explore negative capacitance based device.
I have a question.
Yes.
I was just thinking. So, what are the? Can you tell me, like a brief, a small part? What is the environment condition for the negative capacitance?
So that part I will not be able to answer correctly because it depends on very detailed understanding of physics about the negative capacitance. But if we basically just to give you an answer based on the original work, because the guy who basically found out this, he got a Nobel Prize. I'm not at that level. But the idea is, so this hysteresis behavior is observed by applying certain voltage and measuring charge across a sample of ferroelectric material. So what they did the experiment by keeping all the material properties, because ferroelectric material is not one material. It's a composition of like 4 or 5 different material. Barium is one of them, right?
Yes.
So I'm just trying to find, my student mentioned one of the sample he used for theoretical calculation. It's so it's a composite material, right? So it's actually a composite of at least 4 different types of material. So in this experiment, first they picked one set of composition, barium, oxygen, titanium, and few other things together. They kept material, they changed the temperature, they did the data, and then they kept the temperature and pressure and other thing constant and changed one material percentage at a time. So they changed the material composition painstakingly at a time, and probably for each material they also changed some concentration or different parameters. And after years of testing and trying, finally this guy was able to basically recreate the theoretical observation or the concept of Nobel Prize winner and get this result. Probably he spent his whole life, right? So, but to summarize, it's the factors like material properties, its density, purity, and related compositions, how they are mixed together, like 4 different materials to constitute a ferroelectric insulator, plus the environmental condition like temperature, pressure, right? All those together. So that's the challenge, that how can you achieve that material condition as well as environmental condition to get that negative capacitance. Yes.
I don't know. I'm just thinking some ideas. Just it's pop in my head.
Yeah.
Can we like we know it's in a box, cubic box. They are trying to control the temperature and the pressure of everything. Why don't they make it smaller?
No, it's probably the material sample we are talking about. It's in micrometer range. So they are not basically working on a this size material sample.
It's a small one.
Yeah.
Okay.
Yeah, it is not about being small, or if they know how to control at macro scale, they can scale it down, and that's what happened with transistor, right? Initially they used 3 independent pieces of gold, connected it together, welded it together to form BJT, bipolar junction transistor, right?
Yeah.
And then when we're successfully able to prove the concept and control the electrical property, so when they did the test, originally they did it for maybe 20 volt, and then gradually they scale it down to 1 volt, right? So first, if they know how to control, scaling down will not be a problem. So, but if this type of negative capacitance based devices, if we need to make it real, number one, the the feasibility of this new concept of a negative capacitance is still at the experimental level. So it needs to be lots of new experiment. First, someone need to develop the experiment first for SOI device-based negative capacitance, and then investigate what type of material, physical, electrical, chemical, thermal, mechanical behavior you need and how to achieve that, right? And the other problem is, for any electronic device, there is a static behavior, there is a dynamic behavior during the transition. So how dynamic behavior can be controlled to achieve the desired switching properties. And manufacturing technique, material processing technique, that is the last and the most challenging part. One of the problems in current industry is many device technologies are there in the hand of scientists in the hand of Intel, AMD or companies. They have designed it, tested it, simulated it, and experimentally proven that some devices can be switched at 500 gigahertz. There are hyperjunction transistors that can be switched at 500 gigahertz.
Like a standard.
Yeah. So, but the problem is the manufacturing process. TSMCs and other less than 10 manufacturers across the globe. Their entire process, which they built over last 4 or 5 decades, is for regular MOSFET. So they have to completely rebuild the supply line and processing line and manufacturing room. These are not like a state-of-the-art conveyor belt robot you can buy from store, right? They had to build every piece of robotics for this automated material processing at sub-nano scale. So that's why it is so expensive. These 10 giants across the globe, they built it over 6-7 decades. That's why after US government is spending almost $300 billion for next 10 years under this Chips and Science Act, still they're hoping that US will have some capability
Of producing
in-house, but that's why they're not thinking about building new foundry. They're thinking about enticing TSMC to build a factory in Arizona. They're enticing Intel to open up a new manufacturing facility in Ohio because they already have that capability. Nobody else has that capability. So that is the preventing. It's the reality of designing, implementing, processing and manufacturing new technology. That is what preventing us from taking advantage of all the new cool technologies
already existed.
These are proven.
So this is just from curiosity. So once a time, if the quantum computing, quantum GPs really exist in the real world, then this type of research actually would fare emerging MOSFET. So this type of research will be feasible that time.
Definitely. The question is like, when you talk about feasibility. Now the question is 10 years from now, 20 years from now, somebody else will think that, well, negative capacitance-based device, it looks a very smart idea, but the manufacturing challenges, they will find an equally smart technology, probably that will be easier to implement. So market will pick that. So many brilliant ideas. So we only know the successful one, Bill Gates and Steve Jobs and Mr. Gordon Moore, the founder of Intel. We know the successful ones. We don't know many thousands who tried, even got Nobel Prize, but their concept never came into light, right? So we know only the successful stories. So we never know. People will, like now, quantum computing is now the new trend. So even within quantum computing, how to use this quantum state as logic state. The whole idea is individual atoms or materials, that quantum states, each state can be interpreted as a logic state. And you can achieve many different quantum state phases, and each one can be interpreted as a logic state. So you can make many different variables from the same small device. That's the whole idea. But how to achieve this different quantum space and convert it to a logic interpretation, there are like 4 or 5 different avenues people are exploring, right? So, yes.
So, US government is stuck because the new material sources are coming. They do not have any roadmap to make this. Like, I'm trying to understand. TCMC has all the technology they need, but they don't.
TCMC has the manufacturing capability. TCMC does not have the technology. Intel has the technology. AMD has the technology. NVIDIA has the design. So there's a difference.
Okay.
Yeah.
So TCMC has the industry
Manufacturing
capability.
Yeah.
US government want to do it,
Yeah.
but they are not able to do it because new technology are coming. Those are not manufacturable.
So US
That's the
government,
reason?
first of all, US government doesn't have any technology in their hand. US government, through different agency, provides funding support to universities and industrial entities and individual scientists and engineers to explore ideas. So US government is in the business of generating new knowledge, new ideas and technologies. Different companies, organizations and individuals will hold the patent. But some US agency, as part of the condition, is that like NSF, National Science Foundation. The whole condition, if you invent anything out of this grant, that becomes public property. You have to publish it National Science Depository so that anybody can use it, because they're giving you the money to generate new knowledge and idea for the greater public good. However, US government has an interest to control the access to those new technologies and new ideas, because US government is spending trillions of dollars in generating these new ideas. So US government doesn't want anyone to just grab and copy those technologies, and it's like a drug. Why pharmaceutical drug is so expensive in the USA, not so expensive across the world? Because rest of the world, they wait for 10, 15, 20 years for the patent period to go away. It takes billions of dollars to develop a new drug. And first 20 years, it is a very, very controlled manufacturing of the drug, because pharmaceutical industry needs to recover the billions of dollars they spent in developing the drugs. When the patent protection period is over, now anybody can buy from anywhere in the world. They can buy the manufacturing license and then manufacture in bulk. Then price goes down, right? So, and then US government's agency FDA determines after a few decades, well, now this drug is saturated, all the side effects are well proven, well documented, now you don't even need to protect it. Make it off the shelf, off the counter drug. Anybody can buy it from Walmart pharmacy. So, same thing with this type of technology. The problem is which US government is trying to protect. Intel spent 2 decades to develop this SOI-based FinFET, 18 nanometer FinFET. And if Intel doesn't have the in-house manufacturing capability, they rely only on manufacturing capabilities across the world. There is a high chance of that technology getting leaked or stolen, right? So, these 2 decades of investment, thousands of engineers and scientists who worked behind developing that SOI FinFET, all this labor and investment and ideas will have no benefit to Intel and United States, right? So that's why and also all those TSMC like company, they have limited capability. The volume of production we need across the world, they're not able to deliver it. That's why GM, Ford, Chrysler, Toyota, Honda, 2-3 years ago, in the middle of COVID, they had hundreds of thousands of cars ready, but they couldn't send it to the market because the IC they need to complete the dashboard, inside a BMW dashboard, there are 24 microprocessor, customized microprocessor. In all the newer version, you have more. So like electric EVs are all full of ICs. Less machine, more ICs. That's his electrical vehicle, Tesla, right? So the volume of ICs needed by different sectors, and those 10 manufacturers, they are not able to manufacture. So that's why GM had to shut down many of their plant because they have the car ready, but they cannot send it to the customer because dashboard was incomplete. So to overcome those problems, that's why US government is trying to have those manufacturing plant close by in the United States under their control. So, but probably for the good news is that, let's say for quantum computing device, since USA is working heavily on this new technology, probably USA, if quantum computing becomes a physical option for future computing, maybe some company or some group of companies within USA may come up with first commercial manufacturing technologies. That is good news.
Google is trying.
But the bad news is everybody else is trying to do. European Union is trying to do. China is trying to do. Like nobody thought that DeepSeek will make the whole market turn upside down in 6 hours.
It crashed the Nvidia stock market.
Yeah, because they did the same calculation for $6 million versus $120 million did by OpenAI, right? So, it is very difficult. Like for example, you guys are too young. When first flat screen TV came,
Oh.
They were really expensive.
they were really expensive. I was just waiting for Costco to give like Thanksgiving sale. So I finally bought a 42-inch flat screen TV for $4,000.
4,000.
Now it is like
Oh.
it was like a big deal. I didn't pay $4,000. Luckily, I had a coupon for 30 or 40%. So it was on sale, and then I had a coupon. I ended up paying like $2,500, but tag price was $4,000. So, but now for 42-inch flat screen TV in Walmart sale, you can get for $150, right?
Yeah.
So that means the TV technology. So when I first saw the television, at that time there was no color television. Color television in Bangladesh came around 1985 when I was just crossing elementary school to middle school. So at that time we had from mid 70s to late 70s, before even I was born, there was from early 70s when TV came, there was a 14-inch black and white TV. On one side, it had a radio. On the other side, it had a cassette player. So it is a 3-in-1. A cassette player,
Oh, that would be
14-inch TV, and my father couldn't buy it from a local market. One of his patients went to Japan on a business trip. So that gentleman brought it for my father as a gift from Japan. So at that time in US dollar, it costed about like 1,000 US dollars. So now you probably didn't even see a cassette player.
I've seen it.
You've
I've
seen it?
used it.
Okay. So you didn't use floppy drive, right?
I use floppy
You
drive.
used floppy drive?
I have used many of the stuff. I don't know.
Okay.
I know about the sir.
Yes.
This is called AGMT.
Yeah.
So is it kind of emerging technology for transistor technology? AGMT, HAMT,
Hmm?
HAMT.
Oh, HEMT is actually a much older technology.
Okay.
HEMT is that it is for high temperature, high performance transistor technology. HEMT has been there for more than 2-3 decades. Again, it is aimed for a very specialized application. Yeah. It's also like HBT, hyperjunction bipolar transistor. Those theoretically were there, experimentally proven almost 30-40 years ago. These type of transistors can be operated at 500 gigahertz, but the problem is they are energy efficient. They are very power hungry. That's why nobody used it. So, this is a summary of all the different technologies people are exploring or have explored in the last 50 years or implemented in the last 50 years, and what is the subthreshold swing that was achieved or can be achieved theoretically. Bulk MOSFET, SOI, bulk FinFET, SOI FinFET, all this we have already seen that, right? Up to here, it is already commercially implemented. And this is the theoretical minimum subthreshold swing, 62 millivolt per decade. So this already achieved, and this is the minimum 62 we can go down to for SOI FinFET. Practically, it is in the range of 70 to 80. But this is theoretical limit. And then nanowire FET, we mentioned, going all around with some engineering, material level engineering, they say that it can go down to 35. Tunnel FET or negative capacitance based FET theoretically can go to 13 to 12 millivolt per decade. Impact ion imprisoned MOSFET, they are claiming that it's not even experimentally proven. They're claiming that they can go down to 5 millivolt per decade for ultra low power application. So all these observation up to this, all these theoretical limit, but these are in commercial use. Practically, it is not 62, practically it is in the range of 80, and these are projected. We are not there yet, projected. So these are some of the reference papers used for generating this lecture. So this is a very loaded lecture, so many information. So I suggest each one of you do a Google search or go an IEEE website search and find 3-4 papers on emerging device and material technologies for future nanoelectronics, and then read and educate yourself. So this is, as I said, you will find thousands of papers, but pick a couple of good papers and then start reading. So next week I will introduce a new topic, but before that, let's talk about our paper. Yeah, you have a question?
So the paper, I just want to talk about
Yeah. Yeah, so for this coming Thursday, I just want you to make 2 slides maximum, 2 to 3 slides. Just talk about briefly what basically topic you want to concentrate on. And then some of you already sent me link for your Dropbox or Box folder where we want to put, let's say you picked a topic. Thursday, when you present your topic, I will know. And if I have any good reference paper in my collection related topic, I will put it in your shared Dropbox, then you will basically be able to see.